Hey everyone, welcome to this video. In the previous video, we talked about how we will run our very first CNN. So everything we see in this diagram here. So to get started, please go to the course directory and download this cnn.ipynb file, upload it, and this time we will actually want to use a GPU, otherwise this code will take forever to run, or our model will take forever to run. Go to change runtime type, select a T4 GPU, save, and just do a run all. I've already ran this before, so don't worry about the numbers you see here. And this will take a while to finish, so as it is running, I'll explain what all of the code does. We have our imports in this cell here. This cell, or this code, ensures that we take advantage of the GPU, otherwise this will take forever to run. We will make sure that we normalize our pixel data from 0 to 255 to 0 to 1, and we will work with something called CFAR10. So we'll grab the training data set, the test data set, and we will create our own validation data set by splitting off from the training data set. And our images will be 32 by 32 pixels, and they'll be in color. So here's some examples of what the images will look like. A truck, a dog, an automobile, ship, a cat. And hopefully when our model finishes training, it will be able to accurately guess correctly what these images are. We will use mini batch stochastic gradient descent with a batch size of 64. There will be 703 training batches. And for this cell, all of this CNN code you see here is just what you see in this picture. So feel free to pause the video if you want to make a comparison. But anyways, we have 3 convolutional layers, the last one having 128 kernels. And remember that kernels are essentially feature extractors. We have a max pooling layer, which we will reuse, so we only have to create it once. Then for the classification layer, or the classification part of the CNN, we have a hidden layer, an output layer. The hidden layer has 256 perceptrons. The output layer has 10 perceptrons. So here, one perceptron could be for a cat, another perceptron could be for a dog, and another perceptron could be for a ship. Then for the forward part, we have the learn and extract features part of the CNN, where the inputs are first passed to a convolutional layer. Then it goes through the ReLU activation function, and then it goes through max pooling. We do this 3 times, and our final output here will be 128 feature maps of size 2 by 2. Then for the classification part, we flatten the feature maps and pass it to our fully connected feed-forward neural network. And here I've done a summary of the model so that we can verify things. So after the first max pooling, we have 32 feature maps of size 15 by 15, which I commented up here. But yes, this is just like a good verification of what's going on. Now for training, we're going to specify a loss function of cross entropy loss. And oh yeah, now that we're talking about this, in the classification part, as mentioned earlier in the course, we don't have to explicitly call softmax. We did explicitly call the ReLU activation function. We don't have to call softmax because nn.crossEntropyLoss will do this for us. For the optimizer, we will use Atom, which uses an adaptable learning rate. We'll set a learning rate of 0.001. And now let's start training our model. We'll train it for 10 epochs. All of this that you see here is so that we can check the training loss, the training accuracy, the validation loss, and the validation accuracy during training. Okay, so we will train for 10 epochs. For our training data, we will do a forward pass where we get the outputs, the loss. Then for back propagation, we compute the gradients, update the weights to hopefully be better so we have really good predictions on those pictures or images. And then we do a zero grad to update gradients to 0 for start of next batch. And all of this code that you see here is for, let me highlight everything. All of this code is to compute the training loss and training accuracy during training. During training, we also work with our validation data, which, as I mentioned earlier in the course, think of validation data as like a proxy for what new data could be. And when we're working with our validation data, there's no backpropagation because we do not want to train with the validation data set. So there's outputs, loss, the outputs and loss. And then all of this code is just to get the validation loss and validation accuracy during training. So during our 10 epochs, we see that our weight values actually improve. You go from a training loss of 1.67 to 0.63, a training accuracy of 38% to a training accuracy of 78%, a validation loss of 1.44 to a validation loss of 0.9, and finally, we went from a validation accuracy of 47% to a validation accuracy of 71%. All this means is that our weight values are improving, which is a really good sign. Now, we also discussed in the course that training loss and training accuracy could be how well your student is doing on like study material, and validation loss and validation accuracy could be how well your student is doing well on practice tests. But no matter how well your student does on the study material and practice tests, what ultimately matters in the end is how well your student does on the final test, the final exam. And that's what we will do with the test data set. And the answer is we have a final test accuracy of 69.21%. So about almost 70% accuracy, which is better than randomly guessing, right? If our model just randomly guessed, it would have an accuracy of about 10%. So 70%, not bad. Could be better though. Here I plot some graphs. As we can see, the training loss goes down, but the validation loss definitely starts to flatten a bit and start to increase just a little bit. As for training accuracy and validation accuracy seems to be flattening out as well as we continue to train. And then let's actually see, or let's visualize how well our model guesses these pictures. So it correctly guesses cat, ship, airplane. Although here, it incorrectly thinks that this is a deer. So yeah, I guess in this visualization, it does fairly well, but overall, about 70% accuracy. One last thing I want to mention for this model is that the model could definitely do better if we made some optimizations and changes. But for this course, I want to make this model code as easy to understand as possible. All right, thanks for watching this video. See you all in the next one.